We're going to look at how parametric functions and parametric equations tie in with other forms that you might have seen. The first and probably the most common format for describing a function is explicit functions. This is where the output value, y, is calculated through some explicit calculation that can be done with x. So you know exactly what you're going to do. You're going to take your x value, you're going to do some things to it, and the result will be the y value that corresponds to that x value. So for instance, even if your function is quite complicated, it's something you can still calculate. I give you the input, you do sine of that value, you add a half, and then you take the absolute value of that result. You end up with some weird looking graph in this case, and potentially these functions can be very complicated, but crucially, they are straightforward to calculate. Think of it as the kind of thing you could code into a spreadsheet. So if you had a column of x values, then you could use a single formula to calculate the y value that corresponds to each x value. And from that, you can graph your function, etc., etc. Essentially, this one is an x value that provides and produces a corresponding y value. Implicit functions you've also come across, but only in a couple of forms. The most common time you'll have come across these are probably when dealing with circles. So for instance, x squared add y squared equals 1, the classic unit circle centered at the origin. In this case, it's more convenient to describe the situation in terms of some combination of x's and y's that satisfy a certain rule. It could be written in the way that I've written it here, the more standard unit circle approach, or it would be easy enough to rearrange everything onto the same side and have some function of x and y that equals 0. So that's quite a common way of writing that if you're going to deal with a function like this. These can still be graphed, but they may look a bit different to the other sort. And this is partly because they're not necessarily functions in the strictest sense of the word. You can't necessarily say that for every given input there is a unique output, because in this case it's less like an input and an output and more like two variables that somehow correspond to one another. So if I gave you an x value, you could attempt to solve to find any and all corresponding y values, if there are any. And similarly, if I give you a y value, you could attempt to solve to find potential x values. But there may be no solutions for certain input values for x or for y, and there may be one solution, there may be many solutions. Now, parametric functions are a fundamentally different way of dealing with this situation. You can use them to draw curves just like the explicit functions, but also like the implicit functions, and also like a lot of other things that might be really difficult to put into any sort of Cartesian form. The Cartesian coordinate system based on x and y, or x, y, and z if you're in 3D, is the system that René Descartes came up with, and it works really well, but sometimes it's hard to come up with a direct connection between the x and y coordinates. It may be that those two things are more naturally thought of in terms of some third parameter. This may remind you of when we were dealing with correlation and causation. If we have deaths by drowning connected somehow to sales of ice cream, chances are there's not a direct link between them, so it would be quite hard to come up with a formula that directly computes one from the other. It's not as if selling more ice cream causes people to die through drowning, but what is happening is some other thing, some third factor, in this case the temperature presumably, is causing an impact and an effect in both. When we're dealing with parametrics, we often have this third parameter being t, so I'm going to stick with that for now, and it can be helpful to think of t as being time. So your x and y coordinates, in other words, your position, is determined uniquely at any given moment by the time that's gone by. So in this case, you'd have x as a function of t and y as a function of t. And here's an example. So x might be minus 2 cos t, y could be 1 plus sine 3t. Anything that you can calculate given a value of t. But the crucial thing here is, instead of me giving you x as your input and you getting y as your output, we're provided with an input t and we have two outputs, x and y. And you can create all sorts of weird and wonderful graphs once you start dealing with parametric functions. In this case, the thing to remember is the value of t produces or provides for you a value for x and a value for y, both of which correspond to that value of t. If you look closely on this graph, you'll notice that there is a point that seems to have an x-coordinate of 1 and a y-coordinate of 1, and yet if you imagine tracing this graph, you would go through that point twice. So there are some interesting subtleties to do with parametric functions. In some sense, they are three-dimensional because there are three parameters that are involved in this particular curve. That third parameter of time tells you when you draw each bit. So we can start at the beginning and say the x-coordinate will be minus 2 times cos 0, so that'll be minus 2. And the y-coordinate will be 1 plus sine of 0, which is 1. So we start with a y-coordinate of 1 and an x-coordinate of minus 2. Might surprise you to realize we're starting at the nose of the fish instead of the tail, but that's where this particular function begins if we have t equals 0. And then you can think about tracing forwards in time. So as we go forwards in time, x will become minus 2 times cos of 0.1, minus 2 times cos of pi by 3, etc., etc. And since cos initially starts at 1 and drops down towards 0, x starts at minus 2 and drops, if you like, down towards 0. So x will increase from minus 2 towards 0, but at the same time y is increasing from 1 plus nothing all the way up to 1 plus 1. So it's going up towards 2. We can see the direction of motion here is actually over the top of the fish. We reach this point on the top and we carry on. And if we carry on far enough, we reach this point, the crossing point there between the two branches. That point corresponds to an x-coordinate of 1 and a y-coordinate of 1. So you could solve and find the value of t that corresponds to that point. But you might find that if you track backwards in time from 0, there will be a corresponding point for the negative value of t that corresponds to that positive one. Depending on the values of t that you are allowed to use, you might end up retracing your steps, you might redraw the same thing multiple times, or it might be that you only draw a small part of what is a bigger, more general function. There are lots of subtleties with this and lots of interesting things that we can evaluate and investigate. So that's what we're going to be looking at today. We'll try a few examples and look at what domain and range mean in the context of parametric equations as well. So to start with, if we have a curve defined parametrically and we'd like to see what it looks like in Cartesian coordinate form, then there are often ways we can do this, and the most basic way is direct substitution. So you have an x and a y equation, both defined in terms of t, and you need to find a way to eliminate t. The first step would be to find t in terms of x, or find t in terms of y. In this case, it's not going to be very easy to find t in terms of y, but if x equals e to the t, we can fairly easily rearrange to get t equals ln x. Once we have that, we can substitute it in for y, and we're done. Y equals t squared, but t is ln x, so y equals ln x squared, minus sine of t, but t is ln x, so sine of ln x. It doesn't look very pretty. It's not going to give a very well-known graph, that's for sure, but that is the Cartesian form. And what you're probably already noticing is that it doesn't tell you very much. You can't see very much from this Cartesian equation. Whereas if you look at the parametric form at the top, you can immediately see things like in the x direction, we're getting bigger, faster and faster and faster, but we're never going to have a value that's 0 or negative. In the y direction, there's something interesting going on, which is only really noticeable when t is very small. Because as soon as t gets bigger than about 1 or 2 or 3, t squared will dwarf sine t. So if you're subtracting 1 or minus 1 or something in between, that's going to be insignificant compared to the size of t squared. That's why we see a bit of a wiggle going on at the bottom here, where t squared and sine t are vying for dominance. But then as soon as t gets big enough, t squared is always going to outstrip sine t. This next method is also substitution, but it's a little more subtle. If we've got x equals sine t and y equals cos 2t, you might be tempted to think of t as equal to inverse sine of x. And then we just have y equals cos of 2 lots of inverse sine of x, which is true but limited, because remember, just because x equals sine t doesn't mean that t will equal inverse sine of x. It might be inverse sine of x plus 2 pi, for instance. So the inverse doesn't necessarily give you all the possible solutions. That's the first thing to be aware of. Secondly, there are nicer ways of rearranging this. You're not going to be able to say very much about cos of 2 lots of inverse sine of x. But if we can rewrite in some other clever way, then it might be easier to see what's going on. So in this case, instead of trying to make t in terms of x or y, we want to see if we can identify some other common ground, some function of t that we can write x and y both in terms of. And in this case, because we have cos 2t, there's a formula for that we can rewrite, and the most sensible format for that in this case is 1 minus 2 sine squared t. Then all we need to do is get rid of the sine squared t, because sine t is x. So this is the graph, or is it? Now, one of the dangers with rewriting into a Cartesian form is that it's very tempting to then completely forget about the original parametric form. The parametric form was the true definition and description of your curve, and the Cartesian form is just what you get when you mess around with it a little bit. But although this curve does correspond to the original parametric curve, it doesn't necessarily correspond to it everywhere, and you can't safely extrapolate beyond the values for which the original was valid. And that's something we're going to look into in a bit more detail later, but for this one you should already be able to see that if x is equal to sine t, there is no way x can ever be any value that is not in the range -1 to 1. And y, similarly, will have to lie between 1 and -1, because that's equal to cos of something. Which means that although our curve might be the right shape, it may have extrapolated beyond the bounds that it is entitled to. This one is actually the shape that we would expect to get if we follow our true parametric equation. We end up with x values between 1 and -1, y values between 1 and -1, but the interesting shape which turns into a quadratic, that is there because of the relationship between x and y, and specifically the fact that y is varying at a rate which is exactly twice the rate of x. X takes its time and goes from 1 down to -1, and then it goes back from -1 up to 1, and in the time it takes to do that, while t goes from 0 to 2 pi, y has gone from -1 up to 1, back to -1, up to 1 again, back to -1. So it's doing an up, down, instead of just a left, right. We'll look into that in a bit more detail, and if you've already seen the video on how to graph these with GeoGebra, you can try putting this in and watching it follow the cycle. Take it slow, follow it step by step, see if you can make sense of what it's doing when. The third method I want to show you is probably the favorite one. It can be harder to spot, it can be a little tricky to see what's going on. But this is sleight of hand, is what I call it. Essentially, you're trying to find another clever connection between the two things that you're dealing with. So if you can find a link between x and y, rearrange and use the link. This particular case, I'm using the fact that y is equal to 2 sine t cos t, and x is equal to cos t. Now, if I'd just done a direct substitution, I'd end up with a sine t that I still hadn't managed to deal with. But if I notice that there are connections, if I square things, then I could square x and I could square y. And if I do that, I can start making use of the fact that sine squared t is the same as 1 minus cos squared t. Cos squared t gets replaced directly with x squared, and sine squared gets replaced with 1 minus x squared. Now you might notice that this is in a slightly unusual form. It doesn't say y equals, it says y squared equals. So this is technically an implicit form. And if we wanted an explicit version, we'd have to square root, and we have to be a little bit careful with that. because although you can safely square root 4 and get 2, and you can square root x squared and get x, that doesn't quite tell the whole story. We'd need to incorporate a plus or minus because there are two different equally valid explicit forms for this, and one of them only tells half the story. You need both to tell the complete story. You can try graphing these. They'll look similar to the examples you might have done earlier on in the previous videos, but y squared equals 4 lots of 1 minus x squared times x squared will give you the complete curve, whereas if you only graph one or other of the square rooted versions, you'll only get half of it. You'll get the bit above the x-axis, or if you plot the negative one, the bit below the x-axis. Here's another example. This one involves tan and cos. And if you're trying to find a direct connection between those, with a bit of work, you can do that. What I'm going to do is rearrange x so that I get a tan squared, and I'm going to rearrange y so that I get a cos squared, which can then be turned into a sec squared. If you remember your sine squared or cos squared equals 1 derivatives, by which I mean not calculus derivatives, but deriving alternative formulae, you might remember you can get a 1 plus tan squared equals sec squared. So that's what I'm going to use here. If I subtract 2 from both sides of the x equation and then square both sides, I get tan squared t. I do a similar thing for y. I'm going to add 1, I'm going to square both sides, and I'm going to take the reciprocal. That will give me sec squared. And then all I'm doing here is directly substituting those things into this identity. If tan squared t plus 1 is identical to sec squared t, then x minus 2 squared plus 1 must be the same as 1 over y plus 1 squared. And that's it. As soon as you've got an equation that involves x and y and not t, in other words, you can have x in it and y in it, but you must not have any values of t. They've completely been eliminated. Once you have that, what you're looking at is a Cartesian equation. If the question asks for a Cartesian equation, this is what they're looking for. If they say find a Cartesian equation in the form y equals f of x, then they're looking for an explicit form like this. And in this case, again, it's going to be a bit messy. You've got some square rooting you need to deal with, and so you have to take into account the plus or minus square root for each one. Now we're going to look at what domains and ranges mean. Previously, we've thought of y as being a function of x, and therefore if I have a domain of x values, they will correspond to a range of y values. But now we have effectively a domain of t values. They're the input values that I'm putting in, and then x and y in some sense are both producing a range of values that correspond to the domain of t values. Another way of saying this, which is quite common, is to find the domain and range of y equals f of x. In other words, if it were written as an implicit function, y in terms of x, what would the domain be? In other words, what x values would we need to put into it? And what would the range be? In other words, what are the y values that correspond to those x values? However you think of it, it comes back to the same thing. We need to think in terms of the values of t that go into this and the corresponding values of x and y that come out. So let's start. We look at the function itself. X equals 8 cos t. If t is allowed to be any non-negative number, then that means it will definitely go the full range of 0 to 2 pi, so it will cover the entire period of a cos graph. And 8 times cos t will vary between plus and minus 8 in the same way that cos t varies between plus and minus 1. For y, we need to think carefully about what happens at the boundary. So if t is actually equal to 0, we have 5e to the 0, which is 5. In other words, y can take the value 5. That is at the extreme end, but it can take the value 5 when t equals 0. As t gets bigger, however, it's 5e to the power of minus something. Because t is never negative, e to the minus something which is never negative will always be smaller than 1. And when you multiply by 5, we get the same exponential decay, but it starts from 5 instead of 1. Now, because of that restriction on t, that it's never a negative value, we know for sure that we're never going to get any values that are bigger than 5. But on the flip side, no matter how big or small t might be, we know that e to the power of anything is never 0 and it's never negative. So regardless of what values t was restricted to, we know that by the nature of this curve, it doesn't hit 0 and doesn't go below 0. So we can use that to construct an inequality. We go from 0 to 5, but crucially, we include the 5. We're using a less than or equal to sign here, but we don't include the 0 because we can never quite attain a value of 0. You can get as close to it as you like, but you can't quite reach it. So now we've got the values of the ranges for x and y. We just put them in explicitly like this. X varies between 8 and -8, and it can take and will take both of those values at different points. Y varies between 0 and 5. It can take a value of 5. It can't take a value of 0. With the alternative version, if we're asked for the domain and range, like it says at the bottom of the screen, we could write this in this way. Exactly the same information there, exactly the same working out goes into it, but we're describing it differently. So we're coming back to the original way that we learned for describing domain and range. The domain are the input values, and if we're thinking of the implicit form y equals f of x, the input values are values for x, and then the range is the output values, which are the y values or the f of x values, and they go from 0 to 5, including 5 but not including 0. So the working is the same. You still apply this by thinking in terms of the values of t that can go into each of the two equations, regardless of whether you're eventually going to talk about it in terms of a domain and range for y equals f of x, or if you're going to think of it in terms of the ranges of x and y in terms of a domain for t. The working is the same in both cases. We're going to look next at how we can sketch a curve which is given in parametric form. And it's a very common approach that people take when given a parametric equation and asked to sketch it. They want to convert it into their native language, to turn it into a Cartesian form with just x's and y's and sketch directly from that. And while this is usually a less efficient or sometimes a much harder method, it's not always. So the first thing I'm going to do is show you an example where it can be quite helpful. And then we're going to look at an example where you'd probably find it easier to stick with the parametrics and learn how to work in this new language rather than trying to translate everything back and forth. So let's get stuck in. We notice to begin with that x and y both have a trig function involving t as part of themselves. So I'm going to use the idea of sine squared add cos squared equals 1 to find a way of eliminating t without needing to do anything horrible with inverse trig functions. To do this, I'd like to get cos t and sine t on their own. In other words, I'm going to write cos t in terms of x by doing a bit of rearranging, and similarly sine t in terms of y. Once I've got cos t and sine t, I can square them and add them together, and I know the result will be 1, which means I can square x minus 5 over 2 and y add 3 over 2, add them together and get an answer of 1. So this identity is essentially the cos squared t plus sine squared t equals 1 identity. I've just made the substitution directly, and now we have our Cartesian form. We can make it slightly more recognizable for us by dealing with the fractions. We've got a fraction squared, x minus 5 squared over 2 squared. If I do that with both the fractions, then I'll end up with this. I'm not going to bother sorting out the x minus 5 in a bracket squared. There's no particular benefit to expanding that bracket, so I'll leave it factorized. But I have multiplied through by 4, so I can interpret this more easily as a circle. Center 5 minus 3, and radius, the square root of 4, is 2. So we're done, right? We have a circle, it's got the appropriate center and the appropriate radius. Well, not necessarily. And this is one of the things you have to be very cautious of, especially when you're sketching from the Cartesian form, because this does not necessarily match the original situation exactly. It's the right shape, or at least it contains my function, but it's a little bit like taking an equation which you're trying to solve and then squaring it in order to find the solutions. We've done some stuff with this. In fact, that's exactly what we did do. We squared some stuff to find a nice way of writing this. And while that's not necessarily going to cause exactly the same type of problem, it may well do something similar. In this case, it might have drawn more of the graph than we are entitled to. And you can see that from here, t varies between 0 and pi. So there is a limited number of values we're going to get t to be, and that means there'll be a limited number of values that x and y can be. So the first thing we need to check is that the ranges match what we think we've got already, and it might be that we can only draw a part of the circle after all. Since t is between 0 and pi, cos t will still get its full complement of values from 1 all the way down to -1, because the cos graph manages to make a complete journey from the highest point to the lowest point in just the first half of that 0 to 2 pi period. That means that x is going to take values between -2 add 5 and 2 add 5. So that's going to go from 3 to 7. It looks like that's the complete width of the circle, so we're happy with that one. It's only going to move from 7 down to 3 though. So when we're thinking about which direction things move or where it's going to go, whether it wobbles back and forth, we can see that when t equals 0, we get 7 for our value for x, and when t equals pi, we get 3. So don't be deceived by the order in which these numbers have been written. X will vary, but it will start at 7 and move down to 3. In the y direction, it's a bit sneakier. 2 lots of sine 0 take away 3 will be 0 take away 3, so -3. But by the time we get to pi, the sine wave has done the first half of its loop and it's come back to 0. So we get a -3 again. So while x starts at 7 and goes down to 3, y starts at -3 and goes back to -3. But in between, we get sine of pi by 2, which is 1, multiplied by 2, which is 2, take away 3, which is -1. So the -1, the high point of y, happens somewhere in between. So y goes from -3 up to -1 and then back down to -3. You can look on our picture of the circle at where the point that corresponds to the first -3 might be. Remember, at the beginning, when t equals 0, x is 7 and y is -3. And then as time goes by, x goes from 7 down to 3, and y goes from -3 up to -1, back down to -3. If you spend a bit of time looking at it and thinking about it, you might be able to trace out the journey and identify where on the circle we start and where we finish. Essentially, t only covers the first half of the complete cycle for each trig function, so we get a limited result. For cos, we've managed to go completely from the right to the left, but in terms of sine, we've only gone up and down. We haven't done the subsequent down to the bottom and up again, so we only get this bit of the circle. Our starting point here is the point 7 -3. We move in this direction. We get to the point here with coordinates 5 -1, and we continue, and then we finish when t equals pi right down here at the point 3 -3. Our next example is going to look at how we sketch a curve by looking exclusively at the parametric equations. We're not going to attempt to turn it into a Cartesian form, because even when you get to the point where that will be relatively doable, you don't necessarily generate an equation that's particularly easy to sketch at the end. And even when you do understand and recognize what that equation represents, you'll find that you'll probably still want to come back and use the parametric form to do the actual sketching. It's a much easier way to visualize and see what's happening. There are a few stages to this, so I'm going to work through them one at a time. The first one is to look at the nature of the functions that you're dealing with. We have x and y both defined in terms of trig functions, and we know already how trig functions behave. So it might be a good idea to try sketching the graph of what 5 cos 2x would look like, for instance. Because as t varies, x is going to follow the graph of 5 cos 2t. We can do a similar thing for y, and hopefully you're already noticing that x potentially has values between plus and minus 5, y has values between plus and minus 2. We can look in more detail for the domain that we're provided with, because t is restricted to 0 to pi by 2. So in the x direction, we're going to have a starting value of 5 times cos of nothing, and then a final value of minus 5, because you have 5 times cos of pi. So now we know what x is doing. We start 5 to the right of the origin, and we end up 5 to the left of the origin. Somehow we're moving, not at a constant rate, but following the motion of a cos graph from 5 to minus 5. In the y direction, things are a little more complicated. I've still looked at the endpoints, 2 sine 0 and 2 sine 3 lots of pi by 2, but I've also noted that because it's sine 3t, it's going to be moving up and down 3 times more quickly, with 3 times the frequency of an ordinary sine graph. And even though our domain for t is only a quarter the size that it would need to be to give us a complete period for an ordinary sine graph, it's 3/4 of a complete period for a sine 3t graph. In other words, we're getting the bit of sine that goes up, and then that comes down, and then that goes even further down. So if sine varies from 0 to 1 to 0 to minus 1 back to 0 again, we're getting the 0, 1, 0, minus 1 section. When you multiply by 2, we get 0 up to 2, back to 0, and carrying on all the way down to minus 2. So that's what y is doing as we go along. Starts on the x-axis at a y value of 0, moves up as high as 2, comes back down and continues all the way down to minus 2. The next thing to look at is more detail at any of the important points. And I'm going to try to list these thinking in terms of the t value that produces them, but also the relevance of the x and y values that come out. So the start and end points explicitly will be helpful. So we start with that. We look at t equals 0 to find x and y when t is 0. We're literally subbing in 0 to x equals 5 cos 2t and to y equals 2 sine 3t. That gives me 5 for x and 0 for y. And then we sub in pi by 2. We do a similar thing. We end up with the coordinates as an x and y pair for the end point of the curve. And then we start looking for other interesting things. I've already mentioned what happens with y and how it's worth noticing that there is a maximum. It's very easy to just look at endpoints and think, well, it starts at 0, it ends at minus 2, so it must go from 0 to minus 2. If you don't recognize that there is a change in direction along the way, you might miss some important elements of this. It doesn't just go from 0 to minus 2, it goes to a maximum of positive 2. And by identifying when that happens, in this case, it seems to happen when t is pi by 6, because then when you do 3 lots of t, you get pi by 2, and sine pi by 2 is 1, the maximum it can be. So we get that t value of pi by 6, and we sub it into both the x and the y equations. Then we get the x coordinate of the maximum value for y, as well as the maximum y value. We get 2.5 for x and 2 for y. So our curve goes through the point 2.5, 2. Not only that, but that's the highest it ever gets in the y direction. The other thing to look at is roots or intercept points. And just like with any other graph you've ever drawn, if you want to find out where the curve cuts the y-axis, you set x equal to 0. And if you want to know where it cuts the x-axis, you set y equal to 0. The only difference here is that when you set x or y equal to 0, you're left with an equation in t. So you solve it, you find t. And then you have one extra step where you have to put your value for t into the other one to work out if you've found the value of t for which x is 0. You then sub it into y to find the value of y for which t is pi by 4, because that's the value of t for which x is 0. So you've got a few extra steps in there. But if you know that x is 0, you can find the corresponding value of t. When you know the corresponding value or values of t, you can come back and find the relevant values for y. Be careful when you're solving a trig equation. I've got t equals pi by 4. That was the point within the range 0 to pi by 2 that satisfies this equation. But you want to look out and make sure you found all possible solutions within the range and investigated each of them. That's what happens with y equals 0. There are two solutions I found. T equals 0, which actually is the same as the starting point. And t equals pi by 3 is another solution. And that gives me an x value of minus 2.5. with a corresponding y value, of course, of 0. Once you've done that, it's time to sketch the curve. And if you go through point by point, you should be able to identify the relevant pieces of this. We have 5, 0, which is our starting point. This is where we begin on the curve. And then as we move along, the next point we get to will be the next smallest t value. So we've gone through t equals 0, now we're at t equals pi by 6. That's the point 5/2, 2. So this corresponds to the maximum point on the curve. We've moved smoothly in this direction from the starting point along the curve until we get to the maximum point. If we carry on, the next point we get to after pi by 6 is pi by 4, which is 0√2. So here's our root 2 value. It looks about right on the graph, 1.4-ish. And then from there, we get to pi by 3, the next largest value of t, minus 5/2, 0. There's our minus 2.5, 0 point. And finally, the end, when we go all the way to pi by 2, we have the point minus 5, minus 2, which is the very extreme point here. So now we can see what the motion does, where it starts, where it goes in between, and where it ends up. And even though you may not be able to identify this in terms of a Cartesian equation, because it's not a particularly pleasant Cartesian equation to try to construct or to interpret, even if you do, we can still see by looking in detail at how x changes and how y changes and identifying those key points, we can get a pretty good idea of what the curve is going to look like.